This year, we are honored to host two keynote speakers. Our first 2020 Miriam Mirzakhani keynote speaker is Dr. Dana Randall. Dr. Dana Randall received her A.B. in mathematics from Harvard University in 1988 and her PhD in computer science from the University of California, Berkeley in 1994. She is now a professor of computer science, the advanced professor of computing, and adjunct professor of mathematics at Georgia Tech. She is also an external professor of the Santa Fe Institute. Previously, she was executive director of the Georgia Tech Institute of Data Engineering and Science, IDEAS, that she co-founded, and director of the Algorithms and Randomness Center. Her main area of research is theoretical computer science, particularly randomized algorithms. Please join me in welcoming Dr. Dana Randall, who will speak to us about counting domino tilings of a chessboard, an introduction to counting and sampling.
Thank you, Maria. Okay, let me share my screen. Whoops. Okay, can everyone see my screen? Great. Thank you so much for inviting me to this. I honestly, I've read about the Math Prize, but really seeing all these people here and hearing such inspiring words from people I have admired for a very long time is just fantastic. So I'm really delighted to be sharing this experience with all of you, students, organizers, speakers, and so forth. So yeah, I'm going to tell you about counting, which is sort of the more mathematical side, and sampling, which is more on the computer science side, but they're very, very closely coupled. So why is it not letting me? There we go. Okay. So I'm going to be talking to you about domino tilings. So I'm going to think of a domino as an unmarked 2x1 domino, and I have some region on the square lattice, say a chessboard. This is a 6x6 grid, and I'm placing down dominoes so that every square of the region is covered by exactly one domino. Okay, so this is an example. This is another example of a domino tiling, and as you can imagine, often there's many different ways that you could do this. Okay, so the first question I'm going to ask you guys, I guess hypothetically, is can you always tile an n by n chessboard if I give you a region? And if you thought about it for a minute, I'm sure many of you have seen this sort of as a puzzle. The answer is yes, as long as n is even. So if n is even, you could just use vertical dominoes and fill the region. What if you take that same region, so n is even, but we remove opposite corners? This is a puzzle you might have seen. Can you cover this region with dominoes? So say it's an actual chessboard and you take out two squares. So there are an even number of squares, but the answer is no. And it's no because the two squares I removed from the chessboard are both white. And every time I put a domino down, it covers a black square and a white square. Okay, so I have an excess of black squares, so I can't tile the chessboard. So is it enough that I have a region that has an even number of squares and the same number of black and white squares? And if you play with that a little bit, you'd see the answer is no, you can't. So here's a region. If you look at the leftmost white square, you'll see it kind of needs to be paired with too many different things, and there's no way to tile it. So this was meant to be just a warm-up, an introduction to domino tilings, but I will tell you that there is an efficient algorithm to decide, given a region, if it's tileable, and to find one efficiently if it is. Okay, so this was due to Thurston many years ago. So this would be a fun topic, but I'm going to move on and talk to you instead about counting domino tilings. So we're going to start with an easy problem. So just a simpler toy problem first. So imagine I have a 2x(n) strip and I want to cover that with dominoes. So of course I can cover it. I could just put a whole n vertical dominoes. All right, but I want to know how many ways there are to do it. So this is one way. I'm trying to be cute. Why would you want to tile a strip? So say you have bricks and you're trying to enclose a bunch of bunnies in this little region. So I just have this little strip that's completely extraneous. All right, so I want to know how many ways there are to do it. So I'm going to explore this by just brute force seeing if I could detect a pattern. So when the width is 1, there's one way. I just put down a single tile. When the width is 2, there's 2 different ways to tile. They're both vertical or both horizontal. 3, you would find these 3. It looks like there's a pattern, but it's going to break now. So when I have something of width 4, if you brute force try to figure out how many tilings there are 5. Okay? And now I'm going to go back. I started at 1, but I really could have started at 0. So if I have something of width 0 and height 2, there's only one way to tile it, and it's to not put anything there, okay? So from this very small example that I just did by brute force, the number of walls, or these short strips, are 1, 1, 2, 3, 5. You might see a pattern. If you went a little bit farther, it might become more obvious. Okay, so I have this bunny saying, what is this pattern? And I'm trying to be cute because you'll see that this is the Fibonacci series. Okay, so I'm going to come back to this in a second, but I'm going to tell you why. So if you look at the lower left circle, it has, or where I have the circle, it's in a square, and that square has to be covered by a vertical or a horizontal domino. All right. So I can either tile it vertically or horizontally. And if I do it horizontally, then the space above it has to be horizontal too. All right. But now the remaining ways to tile this, in the upper case, I put down 1 vertical domino. And so if Fn is the number of ways to tile a 2 by n strip, I added 1 vertical domino, and now I have Fn minus 1 are the remaining ways to tile the upper one because it's a little bit shorter. And on the bottom, if I put a horizontal domino and I put the other one above it, I have Fn minus 2 ways to do it. And sure enough, if you look at the series that I have from our hardcore count, from just our brute force counting, it starts 1, 1, 2 is 1 plus 1, 3 is 1 plus 2. So each number is generated by adding the 2 previous ones. Okay, so this is known as the Fibonacci sequence. My obsession with bunnies is because this is supposedly the pattern of how bunnies mate and produce offspring. But mathematically, it's just lovely. So it says that Fn is Fn minus 1 plus Fn minus 2, and F0 and F1 start at 1. And there's a way to solve this recurrence that I'm not going to show you right now, but there's a closed formula, which I'm showing, but it basically grows phi to the n, where phi is the golden ratio, 1 plus root 5 over 2. And you will learn this in college if you take anything related to algorithms or combinatorics. Okay, so we know that if we have strips, the number of tilings grows as phi to the n. Here's another region, which turned out to be just particularly nice. It's called the Aztec Diamond. So we start with 2 squares, and then 4 squares, and then 6, and then 8, and then 10, and I repeat 10, and then I go to 8, 6, 4, 2. So it always starts with 2 squares and grows and then shrinks. Okay, this is called the Aztec Diamond, and I want to, again, brute force experiment how many tilings there are. So when n is 0, the height of the tower, when it's 0, there's one way, you don't put anything down. When n is 1, you have a 2 by 2 square, and they could be vertical or they could be horizontal. So there are 2 ways. And if you brute force pushed it a little farther, n equals 3 gets a little painful, but you'd see 64. So all of you probably are saying, hey, that looks like definitely a pattern, 1, 2, 8, 64. And sure enough, Elkes, Kuperberg, Larson, and Propp proved that the number of these grows as 2 to the n times n plus 1 over 2. It's amazing. Their proof is so lovely. And I especially like this because 3 of the 4 authors on this paper actually were teachers of mine when I was in high school. They were just a few years older, but these are people that when they say that the people you're meeting now, you'll stick with, it's really true, okay? Okay, so we have this very nice number here. Another region you might want to explore the number of tilings for are square walls. Okay, so I have a square chessboard and I want to know how many tilings there are. And here there doesn't seem to be as lovely a formula as the other 2. Okay, so instead what I'm going to do is just see if I could play around with this and get upper and lower bounds for how many tilings there are of an n by n square region. And I'm going to assume that n is even because it has to be. Okay, so what I'm going to do is divide it into 2 by 2 blocks. Okay, so I have n squared over 4 2 by 2 blocks if I divide it with these black lines. Now, each one of these can be tiled in 2 different ways, and every single one of those is a valid domino tiling. Now, of course, there are many, many more domino tilings that don't look like this, where it perfectly subdivides. But we know that the number of tilings includes the set that do subdivide into these 2 by 2 squares, okay? And so that tells me that the number of tilings is more than 2 to the area over 4. Area over 4 is the number of 2 by 2 blocks. So I know I have at least that number of tilings. Okay, so this is just a terrible, crude upper bound, but it's useful. And we can get, okay, whoops. And we could also get sorry, that was a lower bound on the number. And now I'm going to get an upper bound on the number. And this one's just kind of cute. For every square in my region, I'm going to put an arrow pointing north, east, west, or south. Okay. Now, some of those, so there's 4 to the area, 4 to the n squared in this case, ways to put those arrows down. And a small subset of those are going to actually correspond to domino tilings. And it's going to be if you have 2 arrows that always point to each other. So whomever one arrow is pointing to, its partner also points back. So every domino tiling can be represented with these arrows. It's a very small part, but these 2 things together tell us that indeed, like the other 2 things, the growth rate of the number of domino tilings is something that's exponential in the area. We have 2 to the area over 4 lower bound and 4 to the area upper bound. So it's just trying to give us an idea. But for squares, we're kind of stuck. So here is a way to count tilings using an algorithm. I will just say flat out, when I was in high school, if you told me I was going to do anything related to computer science, I would have laughed. And that's, of course, my career now. But I wasn't a programmer. I still am not a programmer. But the math related to computing is lovely. And I was just really drawn to it. And here's an example of why. Okay, so suppose I want to count. This is going to work for any region in the grid. I'm going to describe it for square regions, but here's a generic approach that you could use on any region. So what I'm going to do, I'm going to remind you that this square region is sitting on an infinite chessboard that's colored black and white squares. So I'm going to mark all of the vertical squares on the boundary that have a black square to their right. So I am showing you a particular tiling. Forget the tiling. I'm really now just concentrating on the boundary of the region. And some of those boundary edges are horizontal. I ignore those. Some are vertical. And of the vertical ones, I'm going to look at the ones that have black squares to their right. And that's what I've indicated right here. And now, instead of tiling with unmarked tiles, I'm going to use these 4 marked tiles. Okay? And my rule is going to be that markings have to line up. So if I look at this the upper left vertical one, and I see that there's a marking on the lower left, I know I have to use this first tile because the second one won't match up. The markings won't work, okay? So here I'm going to put a diagonal one, and the next one is going to have to be horizontal. So I started with a tiling, and I end up with a tiling with these markings on it. And what you see are these paths going from left to right, okay? So what I claim is that every tiling of this region, here I'm showing one, but you could imagine many other tilings, every tiling is going to become, when you do this transformation, a set of non-intersecting paths, one path from S1 to T1, one from S2 to T2, and one from S3 to T3, okay? So now instead of counting domino tilings, what I'm really asking you is how many sets of non-intersecting paths are there from the S's to the T's? Okay, so I've just transformed the problem. Now this seems quite difficult too, because I have this constraint that I have many paths and they have to avoid each other. So I'm going to ask a simpler question. I'm going to start with one of the SIs and end in one of the TJs, and I'm going to let AIJ be the number of paths in this green kind of weird shape in this network that starts at SI and ends at TJ. Okay, and I claim that this is something that I can calculate efficiently. It's a method called dynamic programming, but here's all it's doing. So I am hoping you could see my mouse. I've been assuming that. Can you see it a little? Yeah, okay. So I'm starting at S1, and I, from S1, can figure out the number of paths that go diagonally up, diagonally down, or straight across. That's the rules for my paths. And I want to start at S1 and figure out how many ways there are to end at each of the TIs. So there's one way to start at S1 and not go anywhere. There's one way to go diagonally up, one way to go diagonally down. But from here, I have three ways, because I could have gone up and down, I could have gone down and up, or I could have gone straight across. So for each number, each point that I get to, it is the sum of the three previous neighbors to the left. Okay, so I'm going to start there, and I'm just going to sweep across slowly so that I fill in all of those numbers, and I find in the end the number of paths from S1 to each of the TIs are 52, 40, and 10. And now I do the same thing starting with S2. And now I do the same thing starting at S3. So I get these 9 numbers. And when you see something like this, you just automatically should try a determinant. That's a joke. I know a lot of you don't know what a determinant is yet. It's something that's very easy to calculate. It's used in a lot of different fields, often to compute volumes, but there's nothing here even closely resembling a volume. All I'm doing is there's many efficient ways of calculating this. I started with a 3x3 array. I calculated the determinant, and it came out to 1728. And this is the number of domino tilings. Okay, it just blows my mind. So to give credit, this method of counting non-intersecting paths is due to Gesell and Viano and also Lindstrom. The correspondence from tilings to these paths is something that I did in graduate school. But let's see, this should seem completely mysterious. So I am actually, in my ridiculously short talk, going to now give you a proof. Okay, so I know I shouldn't do this, but it's too cool not to show you. So remember, AIJ are the number of paths from source I to sink J. So A11 is the number of paths from source 1 to sink 1, and A22 is the number of paths from source 2 to sink 2. And I'm going to take the product of those two. So I get almost what I want. So on the left, I get the non-intersecting ones, but I'm overcounting if I take that product, and I'm overcounting by the ones that actually do intersect on the right-hand side. Okay, so I've counted too much, but now I'm going to look at what A12 times A21 is. So these are the blue paths from source 1 to sink 2, and the red path from source 2 to sink 1, those have to intersect, okay? And if you go and look at the first place where they intersect and switch the colors up to that point, then you find that this extra thing that has to cross exactly counts the guys that I've overcounted by, okay? So that tells me that A11 times A22 minus A12 times A21, that's calculating the thing on the left that I really want, which correspond to actual tilings. And that is the 2x2 determinant. Okay, so this generalizes. You might want to play with it if you know what a determinant is to try to prove it for 3 paths, but it's just some clever inclusion, exclusion. It gets much more tedious, but this is my favorite proof in the world, so I couldn't resist showing it. Okay, so you now know how to count domino tilings in any region in the plane. Okay, so for the second half of the talk, I'm going to switch from counting to sampling. So I'm going to think of, I have a bag in some sense, this is all hypothetical. I have a bag that contains all the domino tilings of a region I'm interested in, and I'm going to pull one of them out at random, okay? And I want to know how to do that. Why would I be interested in sampling? So before I go on, I will just say that counting and sampling are very closely related. And anyone following polls these days knows that if you can count and you could sample, you know, these things inform each other of probabilities and so forth. So this is a tiling of the Aztec Diamond. Okay, so we mentioned it before. This was the region that went 2, 4, and so forth. It was a power of 2 were the number of tilings. This is a perfectly random selection of a tiling of the Aztec Diamond. So there are 4 colors because remember we have this underlying coloring of the chessboard. So if the tiles are vertical and you have a white square on the bottom, it's red, and a green square on the bottom, or a black square on the bottom, it's green, and the same with the horizontals. So we're just distinguishing those 4 things. And what you find is that there are these frozen regions in each of the corners. Now, of course, there are tilings that don't look like this, but what I'm claiming is that if you chose one at random, it really would look a lot like this, okay? And it's absolutely amazing. Nobody expected this would be true until they came up with algorithms to sample them. And the algorithm that they, or the method they used to count actually let them sample also. So what's more remarkable, if you look at it, you see a frozen region and an unfrozen region. But the curve where it starts getting kind of not yellow at the very top, they call that the Arctic Circle. And there's a theorem that says the Arctic Circle is a circular arc. Okay, so what that means, what they end up showing is that if you take the tiles that are not in the frozen part, this ends up approaching exactly a circle as your tilings get larger and larger. It's remarkable. There's no reason really that should happen. It's led to incredibly deep, fascinating mathematics that people stumbled on completely by accident. Okay, and you could say, what about other lattices, similar problems? So we talked about tilings on the chessboard. There's a closely related problem on the triangular lattice where now instead of tiling with dominoes, you're tiling with these diamond shapes, which we call lozenges. So each diamond is 2 triangles put together, and there's 3 different orientations for them. And I've drawn on the right my 2-dimensional tiling. So this is just a way of putting down these lozenge tilings. And you can't help and look at it, but see it jump out at you 3-dimensionally. And in fact, on the left also, there's a hidden height structure that is just harder to see. Here, you can't help but see it. And if you look at a random tiling of the with lozenges, you again get a circle. And I'm going to show you an even larger one to convince you. This is a perfectly random lozenge tiling, and I hope you can now begin to see that these circles quite naturally emerge, okay? Okay, so Lots of people care about this. We heard from Arun before that, you know, the mathematics you're doing, it's just ridiculous how many things it ends up influencing. So in mathematics, you discover patterns. In chemistry, you estimate probabilities. It's actually related to bond strength for various kinds of for different kinds of carbon structures. In physics, you calculate functions about physical systems. It comes down to the counts of things very similar to this. And in nanotechnology, people model growth processes. And these are all related to the hidden structures that are here. I'm going to skip this slide. So I just want to end by saying a little bit about what does a typical tiling look like, because this is what my research for the last 20 years really has been on problems like this. Okay, so how do we generate a random tiling? I said you want to pull one out of a bag. And you guys use the method that we use all the time when you shuffle a deck of cards. Okay, so I'm going to start with one tiling and I'm going to keep making modifications to it. And I'm going to do it. This is called a Markov chain, but it's a random walk. We also heard about random walks in our very bad joke at the beginning. Okay, so we're going to shuffle our deck of cards. And you know that you start off with a brand new deck. After a few shuffles, it actually looks like it's pretty close to having each of the n factorial, 52 factorial, equally likely. Or at least that's your hope. So here's what I'm going to do for Lozenge tilings. I had been talking about domino tilings. It will be more convenient here where you could see the height structure, okay? So I'm going to choose a vertex at random. I choose this vertex V, and I look and I see it looks like a little cube is missing. I really hope you can all see the three-dimensional structure. I gave this to my 7th and 8th grade daughters yesterday, and they were like, "Oh, this keeps popping out at me." So I'm going to choose a vertex. And if there's no cube, I'm going to try to add it. If there is a cube, I'm going to take it out. And I do that with probability 1/2. And then I repeat. So I have this thing and I'm going to keep adding and removing cubes so that the surface you're seeing keeps changing. So the first thing you observe is that the state space is connected. What's the state space? It's the set of all allowable tilings. And I claim that you can get from any tiling to any other tiling by this method. Once you see it that it corresponds to a set of little cubes, it's easy because I could start at any tiling and keep removing cubes until I get to an empty tiling, an empty box, and then I can add them back in to get to any other thing I want to get to. So once you see the structure, it becomes easy to see that you could reach every tiling by this method. The way I described it, if you do it long enough, each tiling will be exactly equally likely. And I want to get close to exactly equal, but quickly. So the question that I work a lot on is how long is long enough? Because we already argued that there's always an exponential number of these tilings, and we want to generate one quickly. Okay, so a theorem that I have with 2 of my colleagues is that the lozenge chain that I just showed you is rapidly mixing. So in computer science, you learn the fundamental of theoretical computer science is that things on the left, if the running time scales like 2 to the n or 3 to the n squared or something like that, that's exponential time. Those grow way too slowly. So basically, if I'm interested in sampling and n gets to about 17, I'm going to be stuck, okay? On the right, we have things where the growth rate of the amount of steps you need grows like a polynomial, n squared, n to the 10th, n log n. And so the ones on the right are the ones that we're looking for. These are the ones that are actually feasible to implement. And we show that this Markov chain goes into that green cloud and is in fact polynomial time. So I'm just gonna show you a couple of other examples and then I'm gonna conclude. So I know I'm going a tiny bit over, I'll just take a couple more minutes. So I showed you domino tilings early on. So here's a simple Markov chain, a random walk on the set of domino tilings, and it has very much the same theory. The blue is just showing you that these are really common problems that come up in physics, but don't worry about that. So I choose a 2 by 2 square, and if I see two parallel dominoes, right now they're horizontal, I flip them so they're vertical, okay? But if I choose a 2 by 2 square where it's not perfectly tiled by 2, I do nothing, okay? The second problem I'm showing you here is 3 colorings. We haven't talked about that yet, but I have 3 different colors, and any 2 vertices, any 2 circles next to each other are differently colored. And here my process is going to be, I choose a vertex and a color, and I try to recolor that vertex with the new color, okay? But if I choose a vertex where I can't recolor it, I do nothing. So here, it shouldn't be obvious to you that you can reach every coloring, but in fact you can, okay? And on the right, this is called an independent set. So I have a set of blue vertices, but no 2 blue vertices are next to each other. Okay, and I want to generate one of those. So I pick a vertex and a bit, meaning the bit is going to tell me I'm going to try to add or subtract. If I choose this and B is 1, I try to add a vertex there. If B is 0 and there is a vertex, I remove it. And I only add it if it's a valid independent set. And if I choose something and I try to add it, but it has neighbors already, then I do nothing. Okay, so here are 3 procedures. The claim is that all of these are rapidly mixing. These are all good algorithms. So it seems like everything is fast, but that's not the case. So for 3 colorings in 2 dimensions, this is fast. But we've since shown that if you're in high dimensions and you do the same procedure, you will eventually get a perfectly random 3 coloring, but this time it will take exponential time. So this is a slow algorithm when you get above a certain number of dimensions, okay? And independent sets, you can weight them in a way so that it is fast in the place that I just showed you, but if they get very dense, it becomes slow. So I'm just trying to not explain all of this, but give you some flavor of the richness of this field. And this seems sort of mysterious, but the reason I wanted to mention these 2 dichotomies is the difference for independent sets when they're sparse or when they're dense is a phase transition. So you don't have to know a lot about phase transitions, but it's when my algorithms are fast, the set of objects that I'm trying to sample are behaving like a liquid. But when the algorithms become slow, as they are in the dense case, they start behaving actually like a solid. And you can see that the blue vertices are beginning to congeal on one of the sublattices. And so you really see a physical change in this mathematically abstract construct, which is lovely and has all sorts of implications. So I'm concluding by just reminding you what I showed you. Where is there a tiling, if there is one? How many tilings are there? We learned a couple of procedures for counting. Why do we care? Hopefully I convinced you that lots of scientists look at problems just like this. What does a typical tiling look like? And when do we stop our algorithms? So my final slide is, you're going to indulge me. I'm just going to show you that indeed things are changing, which I'm really glad to say. So the top picture is my high school math team. You could see me on the right-hand side at age 17. The lower left is a picture of me with a bunch of my former PhD students, most of whom are now professors. And the third picture are my now middle school daughters when they were younger, and I would drag them along to my office and they would pretend that they could read Springer math books on my couch. So I love that the demographics of who I'm surrounded by has changed a lot. And I thank you very much for listening to me. Thank you.
Thank you, Dana. Thank you so much. That was an awesome talk. I've had the pleasure of knowing Professor Randall, Dana, for more than 20 years, and she's one of top folks in theoretical computer science, and that was a really wonderful talk. We've had a couple of questions come in, and I will ask them, and then I want to encourage more students to feel free to pose questions to Professor Randall. They could be specific about her talk. They can be more broad questions. The best way is to type it into the Q&A box. I think there's also a way you can raise your hand and I can bring you on to the video, but let's see. Okay, this question is from Sophia Barnes. She asks, is there an intuitive way to understand why a circle appears in a random Aztec diamond tiling?
Oh, that's a great question. You know, I can't tell you why a circle is intuitive, but I can tell you why these frozen regions are intuitive. So if you look at, say, you remember your Aztec diamond starts with 2 squares. The top left square can be tiled horizontally or vertically. If it's tiled horizontally, it doesn't force anything else. But if it's vertical, then the one next to it and the one next to it, all of these have to, along the entire side of the Aztec diamond, all have to be vertical. It has this cascading effect. And so it's just, if you do that, you're really cutting down the number of tilings by far too much. So it's basically just saying, with high probability, it has to be horizontal. And you could continue that reasoning. After a while, the reasoning kind of becomes less compelling because you've made a lot of decisions already. So it's not so surprising that you're going to get a brickwork somewhere in the 4 corners. Why it ends up being a circle is completely remarkable. And there are some times that people have conjectured it would be a circle and it wasn't quite. But circles come up a lot. There's reasons to believe that there's some sort of invariance when you rotate things. That would be why circles appear. But the logic sometimes works and sometimes doesn't. So it was a great question.
Okay, super. Thanks to Sophia for asking it. And I have a question of my own. So you talked about tilings in a chessboard, which is a 2-dimensional object. Have people looked at questions like trying to tile a 3-dimensional object, like a 3-dimensional chessboard?
Absolutely, and everything mathematically. I will just say that there's a mailing list that I got on when I was in graduate school on Domino Tilings or something like this that has 1,000 people on it, because people from all different fields look at this problem. It's kind of ridiculous. When you go to 3 dimensions, everything breaks down. So none of the math is there. Even how to connect the state space isn't obvious. So I have a paper, a Soder paper from very early on where it turns out the generalization is not 3-dimensional bricks. It's not 2 by 1 by 1. It's something else. And we forced it so that we would get some of the combinatorial structure. But no, things really break down a lot. So.
Okay, super. And let's see, here comes a question from Cheryl Shu. She asks, what would be your advice for high school students interested in doing math or computer science research?
Do it. It's, I will tell you that not every professor, once you get into college, is keen on doing undergraduate research, but the ones who are get it. And I started in an internship with somebody who I didn't understand the project I was working on at all. It was in number theory, and it was during a summer program. And this was at Bell Labs, where they had a program for women and minorities. And it was probably the first time I did anything that distinguished me by my gender, but what a great experience it was. And, you know, it gave me a chance. He would just give me lectures on different things every day, and it's how I discovered discrete math. So at Harvard, that really wasn't what people were doing at the time, and it made me realize there was this cool field. You know, this random walk that Arun mentioned at the beginning, I think a couple of people have mentioned that, Maria too, is, you know, you start you don't really know what's going to come up. And there are going to be some areas of math you don't like, but just be curious. And I guess I will advise you against, I think a lot of people just think, oh, I'll work on something on my own. And working with somebody who has done this for a long time, they will help you get past the wrong paths more quickly. So it is really useful to just get to work with somebody and kind of listen to their advice on directions to go. So when I work with undergraduates, often there's a programming component just that I could sort of see what's going on, but very often students, undergraduates, realize that they could do the mathematical parts of it. And there's also, when you go to college, there are internships called research experiences for undergraduates. And find one of these, because you'll be in a group with a group of people for a summer who all want to learn how to do research. And the people who run these tend to be very good at finding the right kinds of problems for undergraduates. So I hope that you go into it.
Okay, great. Thanks, Dana. And thank you to Cheryl for posing that question. Here's a question from Saloni Shah. She says, can you talk a little bit about Georgia Tech's math program?
I would love to talk to you at length when you come to Georgia Tech. So, I will offer the same thing that Maria did. Please write to me if you have questions about Georgia Tech, anything afterwards about my talk. It's randall@math.guttech.edu would work. So I started in the math department there. It has grown a lot since I began my career once upon a time. And one of the things that's cool is that this is a graduate program, but we actually have a program that is joint between computer science, math, and industrial engineering called ACO. It's Algorithms, Combinatorics, and Optimization. And so a lot of the students we have, even at the undergraduate level, take some of these courses and get kind of immersed in the fact that discrete math is, it's really discrete math and probability end up being very critical to these three different fields. One of the things that has been useful in being between the two fields is there are more jobs in computer science typically. I'm not saying that's a reason to go into one or the other, but there are, the two fields, there's a lot of overlap in the intersection. And I've probably gotten a lot more opportunities to be on big committees and so forth because I satisfy two diversity check marks at once. I'm from a related field in math, is what theoretical computer science is usually considered, and I'm a woman, and so I'm on a lot of math boards, I have a lot of influence, I have a lot of ways to have access to pretty influential people. So that has actually been a real benefit of, you know, of course, these kinds of benefits you don't really see for the first part of your career when people are wondering why you're in the room. Just ignore it. And you know you're good, you know that you're going to figure it out. And later on, the fact that there aren't that many people who look like you, that's a great thing. So really trust me, it ends up being you learn how to do math and find a career that fits yourself. So that didn't really tell you much about Georgia Tech, but I'd be happy to tell you more specifically if you send me email. But it's a great program.
Okay, super. Yeah, and students, you can Google Dana and you'll quickly find her email address if you did catch it right there. Let's see. Well, here's a question I had. I see you've got a photo of yourself in math team back in high school. I think that's Stuyvesant math, Stuyvesant High School, yes?
Stuyvesant High School, yep.
Yes, awesome. And we have actually many of our students, several of them at least, are on the New York City math team, and in particular at Stuyvesant. That's great. And I think you also did summer programs like the Hampshire College program.
I did. I went to Hampshire twice. And I'm mentioning this because I left the first time. I went after, I guess, my sophomore year. And it was so cool. There were so many smart people. And I left with this just calm of just realizing, oh, I guess I can't do math. I mean, it wasn't like defeatist. It was just like, wow, there's just brilliant people out there. And The next summer, I actually couldn't figure out what else to do, so I went back, and I was one of those people. And it just, something just clicked. So I mentioned this, you know, I knew I was good at math. I was, you know, competing on the New York math team and so forth. And I was captain of the Stuyvesant team. I was the second woman, that my sister was the first. You know, sometimes things just fall into place. And Maria's absolutely right that it's not getting there first. And it's not this competitiveness of, I have to be the quickest person in the room. You know, you just have to see things differently and see things the way other people are not looking at it, and be creative and bring what you have to bring to it. You know, I really didn't think I was going to end up becoming a mathematician, but every time something else came up, it was like, you know, I still want to see what I have, and I kept coming back to it. So.
Okay, well, that's great to hear. Speaking of your sister, I happened to go to a Hampshire College math program with her too, back in 1978.
Wow, okay.
Now, both you and Lisa are prominent scientists. She's a physics professor at Harvard. What was going on in the Randall family that created two such distinguished scientists?
Thank you. I guess that there's definitely a compliment. So we actually have a third sister. Our older sister is, so the oldest of the three girls is learning disabled. And she struggled. I grew up, I was, you know, 5 years younger than Lisa. And so they were close in age. And my parents really instilled in us, you try to go as far as you can go. And that really set an impression for me. Lisa is a superstar. She's the poster child for physics. It's sort of fun to Google her because she's done so many remarkable things. But, you know, growing up with that could have been really intimidating. But really, definitely they expected she would be the academic and I would not. But I just found my own path. And, you know, the more I got away from physics, the more I had people not always asking me if I was her sister, which was a good thing. So I could kind of find my own identity. But, you know, really, my father was a salesman. My mother was an elementary school teacher and stopped doing that because of my disabled sister. So really, there was just nothing remarkable that would set us on this path, except when we loved doing things. In New York City, I was commuting 3 hours a day to get to Stuyvesant for math team at 8 in the morning because I loved it. You know, it was just, I wouldn't be doing it now, but back then it really was a door to a different world that I didn't have access to in Queens where I grew up. And I'm really grateful for that opportunity.
Okay, wonderful. And we got a comment in the chat from Michaela Lynn, who says that she goes to Stuyvesant too.
Awesome. Really good to hear.
Okay. Well, let's see. Maybe I'll just end with one final question before we turn it over for the next speaker. But let's see. Well, if you had to give some advice to your high school self about mathematics and pursuing math, what would you give? Would you do anything different?
You know, being open-minded, knowing that I could have ended up in computer science, like really, I look back and it honestly was an arrogance. I thought, you know, I'm a mathematician. I don't want to actually be called a computer scientist. But also, you know, I think it's just being curious and open-minded. And this might sound stupid, especially since I mentioned that I grew up with this superstar sister. I don't think I figured out until halfway through college that the people who were better than I was at math worked really hard. I just didn't. I mean, you know, I struggled through some classes that I found kind of challenging, but I was almost embarrassed by that because I just assumed the people who were the other people on these math team things with me that I just assumed that they just did it in their sleep. And then I found out that the people who were really good were actually working hard. And I didn't really know how to do that, but I started working harder. And sometimes it's really worth it. At the same time, I will caution you that, I mean, I remember in graduate school seeing the people from my classes in their free time in the library reading math books. And in my free time, I played Frisbee and I read books. And I kind of thought that meant that I couldn't compete because I wasn't putting 100% in, and maybe competing with one arm tied behind my back wasn't the smartest thing, but it's fine. And in fact, the other people burn out and they don't develop these other skills that end up being really important, like knowing how to give a talk, knowing how to go up to people that you don't know and say, what is the real problem? I've been working on this, but what is the thing that your field is really interested in? So a lot of the things that I thought were handicapping myself in graduate school ended up probably helping propel my career. And certainly other people who I thought were smarter just didn't really end up developing sort of a more well-rounded set of skills. So just trust yourself. And I would definitely want to tell myself that start working harder sooner and just have faith that it works out, even though, you know, you don't seem like you think you know who is going to succeed, and it just isn't. And I know it's time to go on to the next speaker. I want to conclude with one other thing. So at Harvard, there's a killer math class you take as a freshman. I mean, it just kills everybody. It's the, you know, hardcore, a bunch of things at once and all from proofs. And when I started that, a lot of people drop out, boys and girls. We ended up with about 4 girls and 20 boys. And the professor, I saw him many years later, and he told me that he did exit interviews. And the guys all said, oh, I'm just too busy right now. And the girls all said, I don't think I could do it. So those of us who stuck through it, of the girls that made it through that killer class, almost all of us became math professors, and almost none of the guys did. So there's something about, you know, getting your stripes, putting in your dues and toughening up that I actually think, I mean, this is of course just anecdotal, but you know, sometimes the adversity and you're kind of learning to try to prove yourself and fight through, it means more to you when you succeed. So I sincerely wish all of you a lot of luck, and I hope I see you at Georgia Tech or math conferences down the road, and you could remind me that you were here.
Yes, awesome. Thank you for the great advice, Dana, and the wonderful talk. Yes, and yeah, maybe in 10 years you will see some of these students at the math conferences, yes, or grad school or wherever. Great. So I am going to turn the mic over to Maria Hamburg, who will introduce our next speaker, but thank you again.
Dr. Randall, thank you so much for such a rich view of bunnies and counting and sampling, but for embodying self-confidence and definitely for being remarkable. Sounds like you always have